Gives me great pleasure to introduce Jerry Schnoor. As you know, he's also a former Clark laureate, as well as a member of the National Academy of Engineering and the head editor-in-chief of ES&T. Jerry is very well known for his mathematical modeling of a wide variety of environmental processes at various scales to inform policy and enable decision-making. And today he's going to tell us about the some water monitoring networks.
Thank you, Pedro. It's a great pleasure to be here today, and I've really been impressed with the conference. And I'd like to thank Jeff Mosher and Gina and Dondra Hill and all the staff of the NWRI for putting this together. I learned a lot. I especially enjoyed hearing from the various water districts. And maybe we should just say, as the last speaker, I can ask for a round of applause for. Really well done. In fact, I feel a little bit like Elizabeth Taylor on the occasion of her 7th wedding day. After all those good talks, it's just a little bit hard to be creative at this point. But I'll try to tell you a little bit about it's really a dream, I guess, of water quality forecasting. We ask ourselves, when you think about environmental engineers as a discipline, really, what value do we give to the public? What do we really try to predict? It's like Yogi Berra said, you know, predicting is easy except when it comes to the future. And we don't do so well at predicting anything. So one thing that maybe we'd like to try to learn how to predict is water quality. And I admit that we're starting very simply, and it's a humble, modest endeavor at this point. But the dream is, why can't we, as engineers, predict someday harmful algal blooms in advance so that we could give engineering warning and control, or people could manage the waters differently? Why can't we take the example that Joan Rose just gave us, what happened in Milwaukee in 1993? Why can't we predict the cryptosporidium and giardia that's coming down a watershed and give advance warning to water operators so that they can either change the treatment practices or maybe vary the sources? Why can't we do those things? And I think the answer is maybe breakthroughs in technology, wireless, broadband, high-performance computing, and trying to gather seamlessly streams of big data from satellites, weather forecasting. And it brings to mind Hurricane Sandy, which just hit the New England coast, and the European models had it much better a week in advance, that it would hit right into New Jersey like it would, and that it would take that left turn. And if you ask, how did they do that? And they did that by using some of those breakthroughs in technology, and I think we can do some of the same. I'm also pleased to be here on the occasion of Pedro Alvarez receiving the Clark Prize Award. Pedro and Rich Valentine in the audience and I were longtime colleagues at the University of Iowa. He's one of my very best buddies. I know that it's certainly appropriate because he's all about water. First, I think it was maybe wastewater, and then groundwater, and drinking water. And in fact, when he's out of water, he's sort of like a fish out of water. Not too comely. But he likes drinking water too, and here you can see that he's drinking, actually with me and some others, a tall, cool glass of treated domestic, well, industrial mostly, but industrial and domestic wastewater in Singapore. And yeah, we thrive on it, and we're all okay. And here to tell you about it. And also on that particular day, my two friends, Pedro Alvarez and Mark Wiesner, we're both at the new water plant in Singapore, as many of you have been, and after drinking the treated domestic wastewater, I think there must be something in it that's good for you, some kind of mega nutrient or something, because we're all 3 Clark Prize awardees. So I'm looking for whatever that is in the water. This is a project funded by the National Science Foundation and a part of our Hydroscience and Engineering Center at University of Iowa, and there's a nice group of us working on it because no one person, I think, knows enough to try to put together the technologies for predicting and forecasting. It's very interdisciplinary. And social science, I'll try to point out, is involved a great deal also, because we need to know how people make decisions and how we might learn from that and maybe even change their behavior in some cases. It's called, it's part of NSF's Cyber-Enabled Discovery and Innovation Program, and while we tried to address all three goals of that, maybe the one that this particular talk tries to hone in on is more the middle one, understanding complexity in natural and built and social systems. Now, the notion of these cyber-enabled big data networks is that there is an awful lot of data out there that we're not taking advantage of. And if you had a data-rich environment, good things can happen. You can do an awful lot towards modeling and prediction and, yeah, maybe even forecasting when you've got, we're talking about petabytes, extremely large amounts of data available to you with which to make sense. And so first we observe, and breakthroughs in nanotechnology, which Pedro and others here are involved with, allow us to have new sensors. They're not coming along fast enough, I might say, but new sensor and sensor networks. And then I guess my part is more on the analysis and modeling part, but ultimately we need cyber infrastructure people who collect the data, make it seamless and interoperable, and build the large databases that allows people to predict things like 7 days in advance where Hurricane Sandy is going to make land. So we're developing a cyber infrastructure that's just really allows us to go from data to knowledge. Just having data isn't enough. We want to somehow learn from it. And part of what I'll show you is that we went to some great lengths to try to understand how farmers make decisions. They're almost as bad as environmental engineers in terms of hurting the cats, but so fortunately we had a lot of some economists helping us with that. And we want to understand the trade-offs that exist. For us, this particular project was on the biofuel economy. As someone said earlier today, 40% of our corn is being used to make biofuels. Honestly, it's really an idiot thing. Thank God for tenure. There's several governors who would have liked to have had my head already for saying that. But indeed, we are using 40% of our, in fact, Iowa is very near to being a corn importing state. We need to import corn just to feed our own animals because such a large fraction of all the corn that we grow is going into biofuels. So that's sort of what this project is, the application of this cyber-enabled intelligent project is about. We're using the Clear Creek watershed. It's just west of Iowa City, so that's rather convenient for us at the University of Iowa. It's only 267 square kilometers. We have other cyber projects at the 50,000 square kilometer size, so more like the Iowa River, Cedar River Basin scale, and we have some urban ones as small as 10 square kilometers, and maybe another time I'll try to tell you about our urban nodes. But today it's largely an agricultural node with 85% of the watershed being in agriculture. Just to give you an idea what it looks like, it certainly would never infiltrate into our stilling basins here in Southern California. It's really turbid and an awful lot of clay and silt content, which is coming from the erosion from the agricultural land. And that's part of our, when you fill up your car with, if you have a flex fuel vehicle with 10 gallons of ethanol fuel, you're filling up with something like, according to our calculations, 40 tons of sediment going down the river towards the Mississippi. That's the equivalent embedded soil erosion resulting from that ethanol fuel. Just a view of our watershed and the corn at an early stage. So the cyber infrastructure part is to try to not only gather all this data that comes from satellites, next-rad radar, flyovers with aircraft, and other aspects. We're using the MODIS satellite in particular, but to try to put it all together seamlessly. And that's the trick, because each data stream comes in different form and has to be assembled such that it can be used in the way that we need for the models. So we do what's called data mining. One of the things we use, in addition to deterministic models, like some you might have used Qual 2 and ModFlow for the groundwater, and SWAT is the main one that we're using for the land use, agricultural. But we use an awful lot of genetic algorithms and neural nets in order to take all this streaming data and to try to draw conclusions or even parameterize the models, either to make input data or to better parameterize the models. And for example, we asked the question, we have NextRad products from our Doppler weather radars, and we can use those, but can we make them better with just a few rain gauges in the basin? If we pay for just a few low-cost rain gauges, can we somehow bootstrap our way to a much better prediction? And I don't have time to go into it fully, but the answer is yes. You can use computational evolution algorithms, and that's just a fancy way of saying neural nets, in order to combine those data sets of the rain gauge network and the NextRad Doppler data in order to make a better prediction. Right now in our 267 square kilometer basin, we only needed 4 rain gauges to improve the prediction quite a lot. From R squared, let's say maybe 0.7 to R squared in above 0.9. This is just showing some of those results. I mentioned that we work closely with socioeconomists, both behaviorists and economists, and that's where the water quality models like SWAT, for example, which has our land use at the resolution of about 30 meters by 30 meters and for the watershed, and we combine it with socioeconomic models. And the socioeconomic models are predicated on trying to get into the farmer's head, how they make decisions, and we use agent-based models for that. Now, the agents could be a water quality manager, maybe in the case I'm thinking of Southern California, how we use. It could be the consumer, what they're exactly doing at the tap. In our case, it happens to be the farmers. How are they applying fertilizers and pesticides? Why do they do what they do? And how might one change practices if practices needs to be changed? So we use local data sources, a lot of sensor technology. Let's see, where's our pointer? Here it is. A lot of sensor technology, and there's still a lot of room for improvement here. We've tested an awful lot of sensors. Right now, what I'm showing you today is really results just for nitrate, for turbidity turned into suspended sediment and erosion rates, and also to estimate E. coli. That's one of the things we'd like to predict a priori and give warning. And I'm missing one, nitrate and flow, hydrology and hydrograph. And that's where the data assimilation and analysis comes from. We have one industrial engineer who just specializes in knowledge services and data mining, because it's an NSF project, so the whole goal is to get as quickly as possible to get the data to the community so that they can use it as soon as it's generated. So in the old days, we used to go out and take samples and bring them back to the laboratory, and in a few months maybe we'd run them, and in maybe 2 years we'd publish that, hopefully in ES&T, for example. But the new model is that it all operates very quickly and at the community scale. As the data streams in, the model is running. And in fact, we do adaptive sampling. We can use the models to tell where to sample, where the information content is highest, and then use that information as it streams in to reparameterize the model so that the models learn and make better and better predictions of the water quality. At least that's the goal. Now the agent-based model, that's the socioeconomic part. It depends on how farmers make decisions. We'd like to get into their noggins and figure out, they're autonomous, very much so. They're very independent. They're heterogeneous among themselves. There's a lot of variability. They can interact with one another and the environment. They can take cues, maybe even cues from a model. So someday we'd like to be able to have them run the model and generate the results and make their own decision. They can learn and they can adapt. So to better define the agents, we had to survey them. We had to pay them in order. Usually we wait until after November so the harvest has come, so they've got some a little bit more time. And we have to pay them a couple $100 to take our surveys because they're pretty elaborate. But we did that in 2010. We asked a lot of questions, hundreds of questions, but these are just some of them. How many more years do you plan to farm? That would be for us like, how many more years do you before you retire, and how many more papers do you think you're going to have to publish before that occurs? Considering your income, where is it coming from, and are you selling to biofuel plants? Do you sell any of your corn to an ethanol plant? Do you invest in the ethanol industry? We're trying to get an idea of their background, and also couple with that with what decisions are they making and how. The agent-based model then has variable decisions. We're interested in what crop are they planting, what tillage practices are they using, deep plowing versus conservation or no-till, what fertilizer rates are they using, and how would those things change, depending on the market prices of the commodity, the fuel, the fertilizer, and so on. And we assume that, and we tested this in the survey too, that what they're trying to do is simply maximize their economic profit under environmental constraints. So with some regulations, they're basically trying to maximize their income. That's what we assumed in the agent-based model coupled with the water quality model. So we can ask questions like, if a farmer earns so much per acre, how much will they plant the next year? If they learn that their soil loss is unsustainable, will they do anything about it? And a lot of the soil losses are unsustainable. If the renewable fuel standard biofuel mandate ceases or changes, how would that change their practices? Things like that. One of the difficulties with all the streaming data is that it comes in all different forms. For example, the SWAT model works on really a farm-based system, but the land use models work on what's called common land use units, and they don't. The polygons in GIS are not the same, so it's a rather big task even to do something that seems so simple as to bring those things together so that we can run the agent-based model, which is based on common land units, and how the farmers are using the land, together with the agricultural runoff model, the SWAT model. So there were 4,376 common land units and 4,000 hydrologic response units in the SWAT model. There were 481 farms, and we have to harmonize all that data. It takes time. And that's a sort of a depiction of how we did it. Now we have virtual farms because they don't any longer correspond exactly to the farmers' farms, and that's good because the farmers don't want to be able to be identified at the 30 meter by 30 meter resolution either, because we're identifying hot spots and really where the nutrients and the chemicals and the soil is running off from. So it's good that it's now a virtual farm. And then we can run scenarios like scenario 1 is the original corn price. Scenario 2, what if we have a 25 or even a 50% increase in corn price. And as you know, in the last few years while we've been doing this project, the price of corn has doubled from $4 a bushel to $8 a bushel. So in that respect, we've run during a very interesting time. We're doing this project at an interesting time. We can look at the change then in runoff, and again, our main variables are nitrate, suspended sediment or soil eroded, and the hydrology. This just shows how the models are hooked together. The agent-based model, the socioeconomic model, is linked with the water quality model, so that the farmer, the agent, that is the farmer, sees the output of their profit, as well as how much soil, nitrate, and everything is eroded, and then we decide whether that changes their decision on how they use the land, and we keep iterating like this throughout, so they're connected. I thought you might be interested in a little bit of the real-time sensing of water quality for a data-driven model. We're taking data every 15 minutes, and it's telemetered back to our computers in the laboratory where the models are running. And these are some of the ones that we've determined are the most reliable. We try to have it be that you never have to go into the field more than once every 2 weeks in order to clean the instrument or maintain it. Otherwise, the people costs are just far too great. So that's our criteria. And these existing sensors pass the test very well, but they're expensive. For just one site, we're talking about maybe $20,000 altogether. Last summer, we had in Dubuque, one of our urban sites, 10-inch rain in 12 hours. A 7-foot wall of water came down. We never used to get 10 inches of rain, and that's unheard of. But a 10-inch rain in 12 hours, a 7-foot wall of water came down our watershed, washed away all our sensor stations. We had 4 of them, and you're just out the money because we're self-insured and there's no replace. So that's definitely one of the pitfalls or drawbacks of this kind of system. This shows after the storm. One of my students, that was one of our instrument packages attached to that pole that he's showing, and the water came up, I suppose, to about his head or so, at least to where the trash is. And it flooded all our solar power collectors and our batteries and everything. But we're able to get very good data every 15 minutes. For example, this is the nitrate flux in Clear Creek. And of course, you get very good estimates of loading, and for the first time, really accurate estimates of how much nutrients the farmer is losing, which is close to 10% of what they apply. In 2008, we had a wet year, which was during this project. The farmers in Iowa alone lost over $1 billion of fertilizer. So we're talking about some real costs that they may or may not be totally aware of. Through linking the socioeconomic behavioral model with the water quality model, at least they know clearly the results of those decisions now. One of the things of interest that's neat is when you have frequent data, like every 15 minutes, you can go back and resample it. So you can ask questions like, well, you can sample it every hour or every day or if normally you would sample at noon once a week. You can resample your data like that and see what do I lose or what do I gain from having a much more frequent signal. And we've asked those kind of questions. I put this in for Joan. One of the things that we are able to predict, but I have to confess that really the gist of it is our standard is 126 coliforming units per 100 mLs is our water quality standard. And really, if you had a model that said when it rains, I'm going to violate my standard, it would probably suffice. But now we have it really quantified and quantitated with all this data, and we can make good predictions of the using through the turbidity measurement to correlated to total suspended solids, and then correlated to E. coli. All we really need for E. coli to make a good prediction, Joan, is temperature, discharge, and I'm forgetting one. And turbidity. If we have those three, I can nail E. coli for you. Of course, we're interested in how much, I mentioned already, how much nitrogen the farmers are losing and the cost to them. We tell them about that. What part of the project is climate change? Our climate is changing, as alluded to earlier in this conference, and it's changing over the decades in very discernible rates. This shows our input from 1958 to 2008 for one of our watersheds, and you can see the precipitation growing through time, and runoff is growing even more than that. I think I'll skip that one in the interest of time. It shows some of the losses from the various watersheds that we're interested in the hundreds of millions of dollars. So we're really talking about a lot of nutrient losses as a result of these high flow events. And in conclusion, we've tried to construct a prototype, so-called intelligent digital watershed for Clear Creek, just a small watershed that I've shown you about. We're using, I didn't have time to show everything, but we're using all of these data sets of digital elevation from Landsat. We're using LiDAR flyovers to get very good information on surface roughness and bank storage and so forth. We're also using MODIS for the when the vegetation greens and so forth. We're using NexRad laser Doppler information and all of this in order to make these predictions. And data assimilation is hopefully improving our model inputs and our parameterizing of the models. And one of our goals is to try to understand the complexity in the human natural system and for farmers' decisions on expanding the biofuel economy, which we're now at 13 billion gallons, almost 14 billion gallons a year. And that's a story that I could spend my whole time on, but I'm happy to try to answer any questions as well. And this is the team for the data that I showed today. This is the team at the University of Iowa. Thank you so much for your attention.